Good morning, good afternoon, everybody, wherever you are. Today we have a special launch of our seminar. First of all, because of the 60th anniversary of birthday of Piotr IHES, who is the founder of our seminar and spiritus movens of many activities around the seminar. Maybe I would ask Professor Dąbrowski from CISA to give a special address.
Well, actually, I'm not well prepared, but I just want to tell you that it's not only that it's anniversary of it, but it's also 25 years of this seminar, non-commutative geometry. Though it was not, of course, at the beginning on Zoom, but just in Warsaw at IMPAN, just Blackboard seminar. So there are two anniversaries, and the 60th birthday of Piotr. Of course, I can just tell that we have a special vegan wine at the end of the seminar of ALAIN, and of course, auguri, buon compleanno, Piotr. Okay.
Grazie, grazie mille. Grazie.
Okay.
Thank you, Ludwig. Thank you, Ludwig.
Okay.
Second, I'm thrilled to announce ALAIN, who is a founding father of all our subject, non-commutative geometry. Today, he will speak about class field theory and Zeta spectral triples. So it's a double delight to introduce you. So please, Alain, the floor is yours. Take it away.
Okay, thank you. Well, the first thing, let me try to turn the pages. The first thing is happy birthday.
Thank you,
Piotr. And I mean, it's a great occasion for me to, first of all, congratulate you for your beautiful mathematical achievements. So this is really what I want to say. But also, I want to thank you. And I want to thank you for these 25 years of seminar on non-commutative geometry, which is really something extremely important for our subject. And I mean, this, this means a lot in the sense that probably the quality of human beings, which I appreciate the most, is persistence. So I am so grateful to you for that. And of course, I am also grateful to the other organizers of this seminar because of the way it is going. And well, in a minor way for inviting me, but I mean, okay, this is a, this is a minor fact. Okay, so I mean, I will explain the following things. I mean, one aspect of this seminar which I really like is the fact that somehow, we are not limited by time. And this gives a possibility to adjust the tempo so that even if one wants to try to say a lot of things, okay, I mean, one can take a tempo which is reasonable. I think one of the things which is difficult in giving a talk is to adopt the right tempo. So I hope I won't go too fast. Anyway, I will reach whatever I can reach. And if you want, the general topic is somehow to understand first very abstract signs which explain what is really going on with this work on Zeta, which I am doing in joint work with Katia Consani and Henri Moscovici. And the second aspect is an aspect which is far more concrete in a way, and which is, if you want, this construction of Zeta spectral triples. And this will be done both at the infrared level and at the ultraviolet level. And when I say that it's more concrete, I mean that thanks to the modern computers, we have, as mathematicians, now the same one aspect that we didn't have before, and which we share with physicists, which is to experiment. So when we have some idea, we can then experiment it with the computer. It can take a lot of time, a lot of computer time and so on, but it's possible. And one thing which I want to tell to Piotr also is the following. You see, when I got 50, I considered myself as totally old and, outmoded and all that. But I took the decision that I should learn how to use the computer. And okay, and I mean, this worked out in the sense that it's like to make a comparison. It's exactly like buying a good pair of glasses. It's not like it's not that it's going to completely change things, but it improves really. It improves a lot of things going on, especially now with the modern computers, which are so efficient.
Do you think we can use artificial intelligence in the future somehow to help us?
Yeah, well, let me tell you this. A small aparté. The small aparté is the following: if you are put off by the C language, by mathematical language, and all that, don't worry 1 second. Just ask ChatGPT, and
Exactly.
she will give you the program, and you will just have to implement it. It's nothing now. Okay, so you don't have to learn. All right, so now let me start the stuff. Okay, so what about class field theory? There is a very beautiful saying about class field theory by Claude Chevalet in 1940. And I mean, so here I have I show you in French, but let me show you the English translation. So the English translation is the following. It says that the object of class field theory is to show how the abelian extensions of an algebraic number field can be determined by elements derived from the knowledge of this field. Or if one wishes to present it in dialectical terms, how a field possesses within itself the elements of its own surpassing. The French is even better in that, because in French you say son propre dépassement, and this has some kind of poetical feeling. But the idea is the following. The idea is that you have all this tower of field extensions, which are very hard to think about, but they can be derived, at least their Galois group can be derived, from the knowledge of the field itself. And the knowledge of the field itself means that since the work of Kummer, who invented ideal numbers, the work of Dedekind, who invented ideals, then ideal classes, and eventually Chevalet invented the ideals. Now, the ideals are, when you divide the group of ideals, which is GL1 of the ideals, by the multiplicative group of the field, and when you divide all that by the connected component of identity, you obtain the Galois group of the maximal abelian extension. This is the main result of class field theory. But when you think about this result, you have to realize one thing. What you realize is that, in fact, it would be wrong to reduce Galois theory to groups and Galois groups. This is not correct. When you look, in fact, at the papers that Galois wrote when he was 17, when Galois was 17, he wrote a paper in which he explained that for an equation which he called primitive, without really defining what it meant, then for this equation to be solvable, it's necessary and sufficient that you can label the roots by the finite field that Galois had invented. The finite field which has a number of elements which is a prime power. So the degree of the equation has to be a prime power. So you can label the roots by a finite field in such a way that the Galois group is contained in the semi-direct product of the affine group of the finite field by the Frobenius. It's unbelievable that Galois 17 stated this theorem, and it took up to the 50s, 1950s, to understand what he meant by a primitive equation. What he meant, which is very subtle, is that the Galois group is acting bitransitively on the roots. Of course, it's always acting transitively, but it's acting transitively on pairs of roots. Okay, so what you understand by looking at this example is that it's not enough to know the Galois group abstractly. You also have to keep in mind how the Galois group is acting on roots. So in general, if you want, Galois theory cannot be reduced just to groups. it has to be complemented by the way these groups are acting on spaces. Now, when you look at the Idel class group, which plays this fundamental role, okay, which is this quotient, GL1 of Adels by K cross, okay?
We don't see the slides.
You don't see the slide?
See,
We see.
we see.
Oh,
You
I
don't
don't
see the
see.
slides.
Maybe.
I can see the slides, yeah.
Yeah.
You see the slides, okay.
Yes, yes.
Riku, I think it's a problem with your new computer.
Yeah, it's a problem with my computer.
Okay, so what I was saying is the following, is that after all, you have this Idel class group, which is the quotient of GL1 of a ring, because after, if you want, the Idel class group, it was found that this group is in fact the GL1 group of a ring, and this ring is a ring of Adels. So the term Adels, I think, was coined by André Weil. And so if you want, this group is not an arbitrary group, it's really the GL1 of a ring. So now the natural task is to see how this group, the Idel class group, is acting on some spaces. What are the natural spaces on which it's acting? Now there is an obvious space on which this group is acting because it's GL1 of a ring. So it's acting on the ring itself. It's acting on AK, the ring of Adels. But on the other hand, the Idel class group is divided by K cross, by the multiplicative group of K. So you have to divide by K. And this is what I was doing in 1996 when I introduced the Adel class space, which is the quotient of the ring of Adels, I mean, which is a space, a locally compact space, by the action of the group. Now, this space is a very delicate space because of ergodicity. Of course, I knew this ergodicity since the very beginning. And it is this ergodicity which makes this space resemble the space of leaves of a foliation and be, if you want, the prototype of a non-commutative space. Now, immediate advantages of this space, immediate advantages are that, you see, class field theory is based on the link between the local class field theory, which is much easier, and the global class field theory. Now, when you look at the local class field theory, what you get is that what replaces the maximal abelian extension is in fact the corresponding group is just the multiplicative group of the completion of the field at the place V. But this group is related to the Idel class group in a very subtle manner because it turns out to be a locally compact subgroup of the Idel class group. Now, from the Adel class space, this becomes obvious because this subgroup is just the isotropy subgroup of the Adel classes which have a 0 at the place V. So if you want this way of relating the local to global becomes geometric, and it becomes exactly the inclusion of an isotropy subgroup inside the full group. Moreover, when you look at the action of this isotropy group on the transverse space to the corresponding periodic orbit, what you find out is that it gives you immediately the term, very mysterious term, which enters in the Weil explicit formula, in the Riemann-Weil explicit formula, for a reason which is ultra simple, which is the computation of the trace, namely the integral of the diagonal values of the Schwarz kernel, of the operation of scaling, which is, if you want, the operation of the Idel class group on the Adel class space. So this is the second point. The third point is that it gave, in 1996, the spectral realization of zeros of zeta and L functions, but as an absorption spectrum, and we shall come back to that. Now, very recently, with Katia Consani, we put a short note in January of this year in which we related the nodes, the primes, and the Adel class space. And Katia has given, in this seminar, a talk about this topic, so I won't talk in details about it, but I will explain further improvement that we did. And this improvement is the following. You see, there has been for many years similarity. I mean, you know, in mathematics, it's very important to know these theories which look alike. There was a looking alike between two theories. One of them was Galois theory. The second was a theory of covering spaces in topology. And Dixmier told me an interesting anecdote. He told me that once in the Cartan seminar in the beginning of the 50s, there was a discussion about this similarity. And Pierre Samuel was negative, and he was telling to Cartan, no, this cannot work because this and that. And then Cartan stopped him and told him, no, it works. Okay. And then, you know, Grothendieck came with the Etale theory. We shall come back to that later, but we won't need it because what we can construct with Katia is a direct construction from an abelian extension of Q to a finite cover of the scaling site. And what we shall see is that it gives a perfect translation from the properties of the Galois extension to the property of the cover, exactly as one should expect in the analogy between extensions and covering spaces. So, I mean, it all goes like this. We have the scaling site, which is the quotient of the Adel class space by the subgroup, which, if you want, is the group which correspond when you take the fixed point to the Riemann zeta function. If you don't take the fixed point, if you take a bundle over it, then you get L functions. But if you want to have the Riemann zeta function, you have to divide by this subgroup of the Adel class group, which is the maximal compact subgroup. Now, this space is a space which you can explain in terms which do not require anything about Adels or anything like that. This space is a non-commutative space. And as a non-commutative space, it is the space of rank 1 subgroups of R. Okay. And I mean, here you just have to think a little bit because when I say a rank 1 subgroup, well, for instance, the group of rational numbers is a rank 1 subgroup. What does it mean, rank 1? It means that any two elements are commensurable. Now, when you consider rank 1 subgroups of R, you could say, oh, wow, I mean, this is a space which I can understand and all that. But I stop you immediately because that's a non-commutative space. So what does it mean to be a non-commutative space? What does it mean in simple terms? It means that you cannot construct an injection from this space to the real numbers. Even though it has the cardinality of the continuum, it's impossible to construct an injection to the real numbers because of ergodicity. Now, in this space, what you have is you have the periodic orbits, which have length log p for each prime number, and which were very obvious from the beginning of the theory. And now what we are going to see is that, well, in a naive manner, and we shall make this more precise, you have to think of this non-commutative space as having a visible part. So it has a visible part, which is what remains of the Adel class group, which is just the group of positive real numbers. That's something which will play the role of the generic orbit. And it has, for each prime, this periodic orbit. What is it? Well, it is a collection of all subgroups of rank 1, which as abstract groups are the same as a group of rational numbers whose denominators are a power of p. When you look at these subgroups, okay, they form a periodic orbit. They form an orbit of length log p. And so we shall gradually understand that this visible part of the scaling site is in fact the points of the hypothetical curve that people are trying to construct since ages that would play the role, if you want, of the curve of algebraic geometry in the case of function fields. So now there is a simple manner to construct a cover when you have a finite abelian group, and when you take a homomorphism from this group, the hat star, to this surjective continuous, of course, homomorphism from the hat star to this group G. Now, if you take such a surjective continuous morphism, you can take the following. You can, if you want, instead of dividing fully by the hat star, you can take the same Adel class space and cross it over the hat star by G. So in doing that, you get a space on which G is acting. It's acting transitively on the fibers. And it's a space which projects on the quotient, of course. It projects on the scaling side, which is the double quotient. So now here is the functor from abelian extensions of Q to covers of the scaling side. So if you start with a finite abelian extension of Q, well, then it turns out, if you want, that you can, of course, you can put this abelian extension of Q inside the complex numbers. The morphism from this finite abelian extension to complex numbers is not unique, but the range of this inside the complex numbers is unique. And so what you have a canonical map from the hat star to the Galois group of this extension. I will come back to that. Essentially, I mean, this is, if you want, the Kronecker-Weber theorem. And it is the class field theory in the case of the rational numbers. So once you have this morphism from the hat star to G, what you have is you have an associated bundle, an associated fiber bundle, and which is constructed just from the previous construction using this morphism. Now, what one can see, first of all, is that it defines a contravariant functor from finite abelian extensions to finite covers. When I was talking about this analogy between extensions and covers, of course, it's contravariant because when you will take a further cover, it will map down, whereas the extension will be included. So it's a contravariant functor. Now, it turns out there is a very simple definition of ramification for covers, and the ramification is the same as the ramification for the field extension. But now comes the whole point. Now the whole point is that if you take an unramified prime, then the monodromy of the periodic orbit in the finite cover is the element of the Galois group, which is given by the Frobenius. And moreover, the connected components of the inverse image of this periodic orbit are circles labeled by the place of the finite extension over the prime P. So the picture is the following. The picture is that you have this periodic orbit associated to the prime, and now in the finite cover, oh, what is it? Yes, in the finite cover, what you have a certain number of connected components when you try to lift this periodic orbit. Each of these components corresponds to a place of the field extension over the place given by P. Now, for each of these field extensions, what you have is you have a cover of the periodic orbit, and this cover has a monodromy, and this monodromy is generated exactly by the Frobenius element. Now, the way this comes about is by Artin reciprocity. So what happens is that you have the Kronecker-Weber theorem, which gives you that every finite abelian extensions of Q is contained in the group of roots of unity, okay? And the Galois group is obtained by raising to power the roots of unity. Okay, so if you want the Galois group of the extension, of the abelian extension, what you do is you put this extension in an extension by roots of unity. There is an optimal way of doing it, which is by the conductor. And then what you have is you have a way to understand the Galois group by this canonical map from the, if you want, the elements of Z mod MZ, which are prime to M as a multiplicative group, they map to the Galois group. Now, the fundamental result of class field theory in the case of the rational numbers is that the Frobenius is equal to the image of the number P under this map. Now, the Frobenius is well defined. This is the reason for the Frobenius to be well defined is the following, is that when you take a prime which is unramified, then everything which happens in an extension, when you take, if you want, one of the places over the prime, everything that happens in this extension is in fact occurring in the residue field. So it's occurring by an extension of the residue field. So it's like the residue field Fp is extended to Fq, and then the Galois group is generated by what Galois knew, namely the Frobenius automorphism of Fq over Fp, which is raising to power. Now, if you want to understand something about the previous theorem is really the fact that when you take this fiber bundle, if you want this bundle over the scaling site, then what happens over a periodic orbit, it's really the mapping torus. It's really the mapping torus of the Frobenius element. So once you know that, then you can prove the theorem. But it's quite amazing that if you want the Adel class space and the role of the prime P fits exactly with Artin reciprocity. We don't have to add anything. It's like the field knew everything what was going to happen for covers, provided you don't just work with groups, with a Galois group. You also work with spaces, namely the Adel class space, okay, and the scaling site in this occurrence. Now, so just to tell you the way you should think about the periodic orbit, let me show you a picture. So if you want, when you look at the simplified situation where you take only two places, where you have the Archimedean place and the p-adic numbers, what you find is the following picture. You find that the way the Adel class space looks, it looks like there is this dense generic orbit, which is, if you want, approaching more and more to the periodic orbit. And it sort of sees it, if you want, as a kind of limit cycle in a way. So if you want, you have this periodic orbit, and you have this dense thing, which is corresponding to Idels. And the very strange thing is that now this phenomenon of being dense, if you want, in this periodic orbit, that the generic orbit is dense in the periodic orbit, reproduces itself when you take several primes. So I won't enter in the details, but the picture is the following. The picture is now, if you take several primes, you will have several of these periodic orbits, but the generic orbit will be dense in each of them. Now you can say, wow, how could this possibly happen? Well, it happens because of, for non-commutative geometers, this should be obvious, in the sense that for non-commutative geometers, what you have to imagine is that for each of these periodic orbits, you have the density. Okay, so you can plot the picture for each of them, and then you can say, but how can it be the same, generic orbit which is dense in each of them? Well, you just take the equivalence relation, which identifies the green for each of them with the green of the other, and then it's done. And to do this identification, of course, you have to use non-commutative geometry, or you have to use, equivalence relations, which are okay with an open set and so on. You can use, here, you could use 3 by 3 matrices, actually, and you would do it. It would work perfectly. Okay, so then if you want, it happened that Grothendieck had also extended Galois theory to spaces, and by inventing the Etale theory. And in our little note with Katia Consani, what we formulated the link with Grothendieck's Etale theory by actually, saying what I have said now about finite covers, but saying it about the projective limit of these covers, and then comparing the Etale fundamental group with the pictures that we have from the Adel class space. And then we understood something. In a way, when you try to work on a specific problem, might be at the end of the day, you have some revelation of something conceptual. And here's the revelation coming from Grothendieck and all that. The revelation was the following. The revelation was that from the start, this work, that I was beginning in 1996 with the Adelic class space and so on. What is it? Well, it is the extension of class field theory from groups to spaces. And in particular, it applies to the Grothendieck-Etale theory. In other words, the Grothendieck-Etale theory has now a counterpart in class field theory. So not only the groups have a counterpart, but also the spaces, and in particular, the spaces of the Grothendieck-Etale theory. And this is extremely satisfactory. Let me tell you why. Because I always had the, you know, like being eaten by a picador when you are a bull or something like that, by the idea that these people in Etale theory are much more advanced than we are, because they have all this theory about spec Z and all that, and they say, you know, spec Z is three-dimensional, and so on and so forth. But now it all falls in our realm, because we can translate what they were saying about spec Z. We can translate it in our language, thanks to class field theory in this way. And we learn something. We learn something because when we look at the way, for instance, you know, at the beginning of Etale theory, there were great contributions by Artin, Michael Artin, I mean, the son of Emil Artin, and also by Mumford and, you know, about
Barry Maser.
And Barry Maser, of course, about the way, if you want, one can do computations with this stuff. And one computation was precisely that the spec of the integers is something which should be thought of as three-dimensional. And the proof, when you look at it, because of course one should look at the proof, you know, when you look at it, what you find out is that it all relies on two things. It relies on class field theory, and it relies on the fact that you have a generic point in spec Z, and this generic point is dense, which is an extremely strange thing. So the generic point is such that it's everywhere dense in spec Z. Oh, but then you come back, and then you say, oh, look, I have this generic orbit. And this generic orbit is dense in all my periodic orbits. So in fact, when you think about it, you find that in fact, people have tried, in fact, there are traces of that on the internet. People have tried to picture spec Z. And they all more or less came up with a picture, not with the periodic orbits, but a picture with points in which the generic point is dense like that. Now, what is the role of the periodic orbits? Well, the role of the periodic orbit is that, of course, spec Z, when you look at spec Z, you are not taking points of the hypothetical curve over an algebraically closed field. You are taking the places, but the places, when you look at the case of function fields, they are just the orbits of the Frobenius. So in fact, these are the orbits of the Frobenius, and they have length log p. The Frobenius is given by the scaling group. And here is the picture of what should be thought of as spec Z. Okay, so it's spec Z taking the points of spec Z over an hypothetical algebraically closed field. And moreover, it reconciles us completely with something which we could have thought totally paradoxical, which is that when you look at the Adel class space, you say, but this is an extremely strange space because the Edels are dense in the Adels. But in fact, this is a blessing because the generic orbit or the generic point is dense in spec Z. And so when you evolve on that by doing more thinking and so on, what you find out is that it guides us because it says that the spectral realization as an absorption spectrum, as I had found it from the start, in fact should be thought of as a relative H1. So in fact, it should be thought of as the action for, this is the spectral realization of all L functions, okay, with the Grossen character. And it should be thought of as a realization in a relative H1, where the relative is relative to the generic point, namely to the generic orbit, which is given by the Edels. So that's, if you want, the conceptual gain from having kind of mastered what people were doing in this approach by the Etale theory. And so what we can be totally reassured about is that with these finite covers and so on, we have the analog of the Etale site that people were using to define Etale cohomology and so on. So we can be reassured about that. Okay. On the other hand, okay, this realization, this spectral realization, was as an absorption spectrum. And so the absorption spectrum, I don't want to spend too much time about it, but the only thing you have to know about it is that this was what led to the discovery of helium, because in the spectral lines from the sun, which were absorption lines, there were some lines which were never identified on Earth, which were missing, like here, in the sunlight. And so physicists or chemists, I mean, were extremely smart people. They invented a physical, a chemical body, pure one, which, because in honor of the sun, they called it helium, and which was characterized by its kind of, signature, which was the spectrum. But then at the end of the 19th century, there was an eruption of Vesuvio. They made a spectral analysis of the lava, and they found that helium was there, which is an amazing fact. Now, what we did with Katya in a paper called the Scaling Hamiltonian, we did the step which was a crucial step in the invention of photography. You see, in the invention of photography, there was first the invention by Nicephore Niepce. What he did was to put a box in front of his courtyard and let it take the light for 8 hours. And after that, he looked, because he had a plate which was sensitive to light. And he got a kind of image of his courtyard after 8 hours of impression. Okay. And so then afterwards, there were improvements which were done by successors of Nicephore Niepce, especially in France. But there was a great contribution which was done in England by William Henry Fox Talbot. And what was the idea of William Henry Fox Talbot? It's a great idea. His idea was the following. His idea was to, instead of taking, if you want, a plate which was sensitive to light and which was, if you want, lighter when there is light and darker when there is no light, he took something which was much easier to fabricate, which was something which was, if you want, which was dark when there was light. And so it was a negative. It was, if you want, it was, so what he took, he was taking negatives, which is exactly the same thing as in an absorption spectrum. So he was exactly taking, if you want, the absorption spectrum version of what he wanted to see. But then he got a beautiful, great idea. Of course, doing this negative was not a great idea. It was just, using another chemical to have an absorption vision. The great idea he had was to take a picture of the negative. That's a fantastic idea. And when he took a picture of the negative, of course, things were reversed, and he got the positive as an outcome. And in this way, he had invented photography, and photography was then developed, for years, exactly following the principle of Fox-Talbot. Now with Katya, in our paper, we did the same thing. So what we did, we took the absorption spectrum version that I had devised, and what we did, we took a picture of it. Namely, we subtracted this negative from the white light. This is explained in great detail in our paper. And so what we got, if you want, we subtracted from the white light, which had a cutoff, the pictures that I had obtained, and then out of that, we obtained, if you want, a picture which was the positive. this picture gave, if you want, as a consequence, a trace formula, which, if you want, I will come back to the previous, but it gave a trace formula in which, instead of having the cutoff as I had in my paper of 1998, had no cutoff anymore. So the lambda disappeared. There was no limiting situation. And so this formula was expressing the veil terms, if you want, in the Riemann veil formula, in terms of operators. Now, the role of this Riemann veil terms is that there is an equivalent way to formulate the Riemann hypothesis, which is the positivity, or rather here it's written as negativity, but you just put a minus in front, of the veil terms. Now, it turns out that as we shall see very soon, it's possible to localize this positivity so that the number of places which are involved is finite. And for instance, one effect that this localization has is to totally dispel, if you want, a belief that most mathematicians have. I think that for most mathematicians, if they were asked, what is the difficulty in proving RH? They would tell you that the difficulty is because there are infinitely many primes. Now, it turns out that because one can localize this positivity, which is equivalent to RH, that's a wrong statement. And in fact, there is a statement which is involving only finitely many V at a time, and which is true if and only if the Riemann hypothesis is true. So what you have to do is to only consider finitely many primes at a time. So there is this trace formula, okay? And this trace formula involves a pair of projections and the angle between this pair of projections. So, I mean, and it also involves a space, which is called the Sonin space. And I mean, Sonin was a mathematician of the 19th century. And I think he got his thesis in Warsaw, in fact. I think he was teaching in Warsaw for some time. And he actually got his thesis in Warsaw.
What was his first name?
This is a name which I cannot pronounce. Let me look. I mean, I will tell you a little bit later. I have it somewhere, okay. But I mean, but he was a great mathematician of the 19th century. Okay, and so in fact, the trace formula that you get from this transformation from the absorption spectrum into an emission spectrum is a formula which involves two terms. It involves one term, which is the Sonin term, and one term, which is the prolate term. And what we did with Katia Consani a long time ago, I mean, some time ago, this was in 2021, okay, looks a long time ago, was to prove that if you restrict functions, test function, with this condition on the support, then you have the negative or the positivity property, if you want, and it comes from the Sonin space. So if you want, the reserve of positivity is due to the Sonin space. The other difficulty is not coming from Sonin, it's coming from this stupid little square here. So in other words, when you look at the trace formula, you find that positivity is guaranteed by this infinite square here, but there is a guardian of the difficulty, if you want, which is here, and which will prevent you from concluding. And it's coming from this little square. And the reason why this guardian has to be there is that if it were not there, then the positivity would hold unconditionally, but it doesn't hold unconditionally. What I mean is that it's crucial in our proof with Katia that we have the support condition on this function because we only look at the Archimedean place. And when you look further, so as I said, I mean, you localize the veil positivity. When you look further, and we did with the computer, what you find is something which is absolutely mind-blowing. What you find is that when you look at this veil quadratic form, which you could prove to be positive when you restrict to functions which have support in a small support. So when you look at this Weil quadratic form and you restrict functions to have support between lambda inverse and lambda, that's why I put a lambda here. Then when lambda, here is lambda square here, in fact. So it's mu. When this mu increases, okay, I have put here the log of the smallest eigenvalue. So for instance, when lambda is equal to 5, you find that the smallest eigenvalue of this Weil quadratic form is of the order of 10 to the power minus 123. So this means that it's number 0.0000. You have 123 zeros. And then you have a small thing, okay? Now you can say, well, okay, first of all, why don't you get exactly 0? Well, you cannot get exactly 0. This follows from the Nevalina's theory, or if you want, it follows because if you assume RH, then the smallest eigenvalue of this Weil quadratic form, you know that it's strictly positive. It cannot be 0 because if you want, if it were 0, or the point is that if it were 0, then the Fourier transform of this eigenfunction would vanish at every 0 of zeta. But there are too many zeros of zeta for this holomorphic function, which is of exponential type, to vanish at all these zeros. So it's impossible. So you know it's impossible. You know it's impossible. And you are in front of a dilemma because in the work with Katya, we were using, and in fact, this had also been sometime before by Yoshida, we were using the computer. So, I mean, here, of course, you cannot use the computer. It's impossible. Because how can you know that the computer is delivering a positive result if you have the first zeros, which are 123 of them? This is impossible. Okay. So if you want, the difficulty is coming from the prolate part. And the prolate part is coming from the analysis of the angle between two projections. And this analysis, I don't want to spend too much time on it because I gave many talks on that. This analysis is between two projections, which has been done by Slepian and his collaborators in the Bell Lab in the 50s. And they were working in communication of signals. And what they were trying to do was to find a way to optimize the transmission of signals, knowing that when you transmit a signal, you have, if you want, limited time, and you have limited frequencies. So this means that you have a limitation on the time, which is this projection P lambda, and you have a limitation on the frequencies, which is this projection P lambda at. And what Slepian and his collaborators found, they found that they could diagonalize this operator, and so they could compute the cosine square of this angle using an operator, which I will come later to, which is the prolate operator. And the bare fact, which I ask you to contemplate, is that you have the same minuscule behavior. In other words, when you look at the difference between 1 and the largest eigenvalue of this operator, okay? So this operator is an operator which is the product of three projections, but it's the compression of a projection between another one. So it's between 0 and 1. And so when you look at the spectrum is between 0 and 1. Now you look at the largest eigenvalue, and you look at the difference between this largest eigenvalue and 1, and you find exactly the same behavior as you had for the minimum of the Weil quadratic form. Namely, when you look at the log of this difference, you find the same numbers. So you find, for instance, that, you know, when the mu, which is lambda square, is 25, so when lambda is 5, you again find 10 to the minus, in fact, you find even a little bit more smaller, 10 to the minus 124. Okay. So what we did then was to look, so you can look at the decay of the corresponding eigenvalue of the Weil quadratic form. And then there is an understanding of why you get these extremely small eigenvalues of the Weil quadratic form. And the conceptual understanding is the following, is that if you would look at the full Weil quadratic form, not with restriction of support condition, then it has a radical. So, and it has a radical which is given by functions which are obtained in this way, and which we shall soon relate to the Riemann sums of an integral. So it turns out that when you take functions of this form, they are, because of the Poisson formula, they are in the radical of the full Weil quadratic form. And then if you try to force them to have compact support with Fourier transform of compact support, it's not possible, but it's almost possible due to the work of Slepian and his collaborators. So experimentally, what one finds is the following fundamental fact, that when you look at the space of eigenvectors of k lowest eigenvalue for the Weil quadratic form, QW lambda, this corresponds to something which is computable and which is given by the prolate functions of Slepian and his collaborators. Okay, and using this fact, this was what we were doing with Katia a few years ago. So what we tried to define a spectral triple that would be a good spectral triple for the infrared. We tried that. And I mean, I will explain briefly what we did, and then I will explain less briefly what is the good spectral triple for the infrared. But we are not yet there. This is what we were doing in a paper with Katia dedicated to von Jones. So what we tried to do with Katia was the following for a spectral triple. We were taking the quotients of the multiplicative group by powers of mu. So if you want, we were taking periodic boundary condition for the scaling operator, which is given by IU d by du. And then we were compressing this operator on the orthogonal of this prolate projection. So, you know, this was an attempt. So what we had in mind was the following. After all, this prolate projection gives you extremely small eigenvalue of the Weil quadratic form. So we force them to be there, and then we take the scaling, because we know that it is a scaling operator, which has to be the right operator. Okay. And then we made experiments with this. We made experiments. And when we began making experiments, we were quite excited, because at the beginning of the experiments, we were getting something which was looking like the spectrum of Zeta, which was looking like, if you want, the zeros of Zeta. But after a while, we found that when we were varying, the problem was the following. The problem was that we just didn't have a single operator for each lambda, because we had to make k conditions, and the number k was not fixed from lambda. And the number k is an integer. So when you jump from k to another, you know, something happens. So in fact, what we found after a while was that it's not true that we were getting the spectrum of Zeta, but what was true is that when we were looking at the eigenvalues, these eigenvalues were meeting when we were changing the number of conditions, and the places where they were meeting was here the first zero of Zeta. And then we looked at the place where they were meeting further on and so on, and we got the second zero of Zeta. Then we understood that there was a quantization condition. I go very fast here because this is not the point of my talk. I'm just recalling something, which is in our paper. And then, so after a while, what we found is that, in fact, we were getting zeros of Zeta, but in order to get zeros of Zeta, we had to adjust the wavelengths of our experiment, because since we were taking periodic boundary conditions, we were forcing the spectrum to be in a certain lattice. And so we had to adjust the wavelengths, if you want, of our apparatus in order to catch the zeros of Zeta. So this was good, of course, and we got a mathematical theorem, okay? So we got a conceptual explanation of that. We got a corresponding mathematical theorem. The corresponding mathematical theorem was that, in fact, there was a notion, there was an abstract notion, which was the notion of Zeta cycle. So in other words, there was a way to introduce abstractly what are Zeta cycles. So what are they? They are a circle of lengths, fixed lengths, circle of given lengths, which is such that when you look inside the circle to the space of Riemann sums rescaled by mu, Riemann sums of arbitrary functions, you get a subspace which is not dense in the Hilbert space of L2 functions in the space. So that's an extremely simple condition. And then the theorem that we got was that if you take a zeta cycle, and if you take the action on the zeta cycle of the multiplicative group, then the spectrum is formed by imaginary parts of zeros of zeta on the critical line. And conversely, if you take a critical zero of zeta, then there is a corresponding zeta cycle. But as I said, this was not fully satisfactory because it was not giving you an operator which has the right first zeros of zeta. No, it was giving you an apparatus which you could use in order to find the zeros of zeta, which is quite different. Okay, so now here is the new idea which we have found, I mean, with Katja and Henri in our, and the new idea is coming from a totally different place, and it's coming from the Toeplitz paradigm. It turns out that when you look at Toeplitz matrices, there is a fantastic result. I think it's due to Zego, but I'm not sure. I'm not sure about the paternity of this result. But this result is like, if you want, an RH, I mean, a tool for RH. This is, if you want, the second thing which I would like to say to if you have people and, for instance, they tell you, oh, yes, Riemann hypothesis is coming from the infinity of primes. False. If they tell you, well, Riemann hypothesis, we don't have any tool. False. Here is a great tool. The great tool is the following theorem. Tells you that if you take a Toeplitz matrix, any self-adjoint, which is positive, okay, and if you assume it has a one-dimensional kernel, then the polynomials that you get from the lowest vector in this, from the vector in this kernel, has all its roots on the unit circle. And this means, for instance, that you can take, you know, what people do with the Riemann hypothesis in function fields. You can take their Toeplitz matrix, and out of their Toeplitz matrix, you can take the lowest eigenvector. It always exists, doesn't need to be positive, because you just push the matrix to be positive. Then this vector satisfies RH. In other words, the corresponding polynomial has all its roots on the unit circle. And I tell you this for good reasons. I tell you because I was computing, when I was trying to illustrate, if you want, the Riemann hypothesis for function fields with music, I was computing with hyperelliptic curves and polynomials and so on, and I was always very struck to find all these polynomials which have all roots on the circle. But what is true is that, in fact, it's not something so great, because it's something you get automatically from a Toeplitz matrix. So I find this extremely striking. And I mean, we used it in our paper with Katja on the Veil Archimedean case. We also used it in the work with Walter Weinzel-Lecombe for operator systems. Now, okay, so now what we have in the work with Henri and Katja, we have a C-star algebra proof of this result, which, because it's a C-star algebra proof, has all the reasons to be possible to extend to the continuous case. And what is this proof? Well, the proof is the following. The proof is that you take this real symmetric positive semi-definite matrix, okay? And you take a non-zero element of its kernel. Then what do? Well, then you consider the ideal in the Laurent polynomials, which is generated by this polynomial. The polynomial whose coefficients are the coefficients of the element in the kernel. And then what you prove, it's not so difficult. You prove that there exists a unique linear form on the quotient by this ideal, which fulfills the condition that when you evaluate it on monomial, so it's a kind of moment problem. So you prove, if you want, that there is a unique linear form satisfying the moment problem for this xj, which are the terms which enter in the Toeplitz matrix. Moreover, you prove that this linear form is positive on the quotient algebra. Okay, and the proof is not really difficult. I mean, it comes from the positivity of the Toeplitz matrix. It's really an easy statement. Now, from C-star algebras, what do you deduce? And from the GNS construction. So from the GNS construction, what you have a linear form, which is positive, which vanishes on this ideal. It defines, in fact, a positive linear form on the full C-star algebra, which is the C-star algebra of convolution of the group Z. And so it defines a positive measure on the dual, U1 of Z. Now, this measure is supported by the n eigenvalues of the unitary. And these eigenvalues are exactly the zeros of the polynomial. I mean, this is a very easy check. So what you have is that just by unitarity, you get the RH, namely you get that the roots are of modulus 1. So you get it from a completely conceptual abstract proof. This is an essential step. Now, what one has, and what we use, okay, with Henri and Katia, is a dictionary between the Toeplitz case and the Weil quadratic form. So in the Toeplitz case, you have this Toeplitz matrix, which is discrete. Now, in the case of the Weil quadratic form, you have the distribution, which is given by Weil. There is a nuance, which is very important, which is that in the case of the Toeplitz matrix, you can get a state on the C-star algebra. Here, you get a weight because of the singularity of the Weil distribution at the origin. So it's a little bit more difficult. But then you have what corresponds to the Toeplitz matrix is the Schwarz kernel given by the Weil distribution. The Toeplitz quadratic form is the Weil quadratic form, of course. The companion matrix, which plays a key role in the case of the Toeplitz theory, is replaced by a certain operator. The zeros of the polynomial are now the zeros of the Fourier transform. Okay. So, I mean, now we are getting really to something. And the unitarity of the operator, which is coming from the unitarity of the C-star algebra representation, is coming from the self-adjointness of an operator for the quadratic form. And so now we have our candidate for the Zeta spectral triple. So here it is. So now the space of the algebra is the same. The algebra is the algebra of smooth functions in the interval lambda inverse lambda, okay, where mu is the square of lambda. The Hilbert space is more delicate. Yes, the Hilbert space is the completion of the smooth functions for the inner product given by the Weil quadratic form, but you have to shift the Weil quadratic form to put its minimum to 0. That's easy, okay? So that doesn't assume that it's positive. We have shown that it's lower bounded, so this is always possible. And the operator is just scaling. So if you want, this is quite amazing because it's the same operator as we were using with Katia, but the Hilbert space structure is changed. The algebra is the same, but we do not put the periodic boundary condition. The only change is in the inner product. Okay? And now what you have a picture in the Fourier transform. Why? Because the Fourier transform of the C-star algebra of convolution of functions on R plus star is just multiplication of functions on the dual group, which is R. And what you find is that the spectrum of this operator is given by the zeros of the Fourier transform of what? Of the eigenvector for the lowest eigenvalue of the Weil quadratic form. Okay. And so now you can be back to the working table. You go back to the computer and you say, oh my God, now I was able to compute the eigenvector for the lowest eigenvalue of the Weil quadratic form. What will happen for its Fourier transform and its zeros? Okay. And here I have to recount a story which happened when we did the computation. It's a crazy story. So when we started doing the computation, didn't look good at all. In other words, we were getting functions. These functions were coming from the lowest eigenvector of the Weil quadratic form. And when we were looking at their zeros, they were looking like nothing, except for one value, very strange value around 22, oh, there were a few first zeros which were looking like the zeros of zeta. And because they were looking so close to the zeros of zeta, it was impossible to think that this was just a coincidence. Okay, so then the idea was to redo the calculation. So the computation had been done with 40 decimal places with the computer. And the idea was to redo the calculations with 80 decimal places with the computer and see what happens. And when we redid the calculation in this example with 80 decimal places, the good zeros had disappeared. So in other words, after doing that, the good zeros had disappeared. So this was really a catastrophe. On the other hand, it was like there was a devil which had shown us that there was something in this story. Okay. So for several days, we were totally mystified, except that when there were these good zeros, the function that was obtained had a first component which was vanishing almost. It was extremely small. So then we got the idea of imposing that this first component would be 0 as an additional condition. And then we redid the calculation with this additional condition, and it worked marvelously. It worked marvelously. Okay? And this was the situation again for some time, perhaps 2 weeks or 3 weeks. Okay? And after 2 or 3 weeks, finally, we understood that there was a computer mistake in the calculation, which was giving the wrong value of the Fourier transform for this when this component was not 0. So after correcting this computer mistake, then we could go back to the working table. You could say after wasting 3 weeks, okay, fine. But this is what physicists do when they do experiments. Of course, they do mistakes. And the whole point is to correct this mistake. So after correcting this mistake, we were back to the working table. And we were back computing again the zeros of the Fourier transform of the eigenvector for the lowest eigenvalue. And I must say, I mean, this is an answer to Piotr. I must say that in order to compute these zeros, I had to ask ChatGPT. Why? Because, I mean, I didn't know. Of course, I have Mathematica and I've been using Mathematica for years. But in order to compute several zeros of a function, I didn't know how to make a good program. And what ChatGPT told me is that, oh, well, it's simple. You have to make a grid with a lot of numbers, ask when there is a change of sign of the function between two. And once you are in this interval, use another program to focus on the zero. That's what she told me. Okay? So then I used what she told me, and I began to compute. So this is a graph of the Fourier transform that you get for a small value of lambda. Lambda equals 3. Okay? But you look now at this graph more precisely. What do you find? Oh, this function is cutting close to 14. Close to 14. 14 point something is the first zero of zeta. So this function is cutting close to 14. What about the next one? You look at the next one. Oh, it's now crossing close to 21. And then close to 25. Okay? Of course, these numbers are very small. Okay? And now you ask, using the program of ChatGPT, you ask, okay, and now you can continue with 30 and so on. You ask ChatGPT, please compute with this mathematical program, compute my zeros. And here is the zeros that you compute, and here are the true zeros. The first one is 14.1347. In fact, there are 15 decimal places which are the same as for the zeros of zeta. This is just for lambda equals 3. Okay, and you keep going, 21.022, 25.0109, okay? And it keeps going like this. it goes astray after a while, well, which is normal after a while. I mean, you can, so it goes astray when you are reaching the end. I mean, around here, I mean, it goes astray, but very small. For instance, here is 72.0648, and here 72.0672. I mean, it goes astray, but it's amazing. It's amazing because when you compute the number of good decimal places that you get, you get something which is unbelievable, which is truly unbelievable. And in order to check that what you have done for lambda equals 3 continues, in fact, to hold for all values of lambda, what you do is, okay, now you take the computer, you use 16 kernels to do the computations. And here are the computations of the zeros of the functions that you get, Fourier transform, for when you take the square roots of these numbers. So lambda square belongs to these sequences. And what you get is that perhaps at the beginning, okay, it's not perfect, but after a while, it's really perfect. So what you have in doing this, if you want, what we have achieved is now we really have, if you want, a perfect candidate for the infrared of the zeros of the Riemann zeta function. All the more because the next issue, if you want, is to completely get rid of the veil quadratic form, because after all, the construction was really, the main thing that it was using was the lowest eigenvalue eigenvector. And because of the work on prolate functions, we have a candidate for this lowest eigenvalue eigenvector. So in other words, now, if you want, we have an understanding of the infrared part of the zeros of zeta using the prolate wave functions, not yet the prolate operator. I'm now coming to the prolate operator, namely to the ultraviolet behavior. And the ultraviolet behavior, this is joint work with Henri. And I mean, in this work, if you want, it was again something which is a kind of miracle what happened, in the sense that what we did with Henri was to start with a problem which a priori had no relation whatsoever with the Riemann zeta function. And I always take this example as the prototype example of a work which, if you wanted to write a proposal for the NSF or now for the European stuff and so on, okay, I mean, it would be impossible. It would be impossible because, I mean, to think that we mathematicians can write proposals in which we are going to say what we are going to find, when we are going to find, and so on, this is absolutely ridiculous. I mean, what matters is that, if you want, we always try to work on conceptual problems, but of course, having no idea of what the results of our investigations will be. So if I have time, I will come back to the heat expansion and zeta, but I prefer to really go to the prolate operator. So going to the prolate operator, if you want, what happens is the following. So what happens is that, first of all, there was this discovery of Slepian and his collaborators that, if you want, the diagonalization of the angle operator between the projections p lambda and p lambda hat was possible because they were commuting with the differential operator. Now, if you want to understand why they commute with this differential operator, it's very, very important to have a mental picture, and that's what I want to explain. What is the mental picture between the fact that there is an operator, differential operator, that actually commutes with the two projections? Well, the mental picture is the following. Let's take a semi-classical picture. So in the semi-classical picture, when you say that you are localizing between minus lambda and lambda in the Q space, what you have is you have two lines in the phase space which are bounding the interval from minus lambda to lambda. When you say that you try to localize the function so that the frequencies are localized between minus lambda and lambda, what you have is other two lines, which are the lines p equals minus lambda and p equals lambda. Okay. Now, how can it be that by staring at this picture, you will guess a differential operator that commutes with the projections p lambda and p lambda hat? Okay, that's my that's my question. Let's just stare at this picture. Now, when you stare at this picture, you say, what do I have? I have four lines. What is the equation of the union of these four lines? Well, the equation is q square minus lambda square times p square minus lambda square. It's an equation of degree 4. And when you solve this equation, you get the four lines. So the zeros of this product are exactly the four lines. Okay. Now, what do we learn when we learn semi-classical approximation and when we learn Hamiltonian mechanics? We learn that if we take an Hamiltonian, the flow lines of the Hamiltonians will preserve the levels of the Hamiltonian. So in particular, if I take the Hamiltonian, which is given by p square minus lambda square times q square minus lambda square, the flow lines will preserve these four lines. This is the picture. This is the picture of the flow lines of the p square minus lambda square times q square minus lambda square. You see that these four lines are preserved. But what does it mean that the flow preserves these lines? It means that the flow commutes with the two projections. Okay? So it exactly means that the flow coming from the Hamiltonian h lambda of pq equals p square minus lambda square times q square minus lambda square preserves the four lines and then commutes with the two projections. Okay. Now the prolate operator, okay, is up to a constant, which doesn't change, of course, the fact that it commutes, a multiple of this Hamiltonian, and then you add a constant. Of course, this is a semi-classical picture, and you could argue, yes, P and Q do not commute, how do you quantize, and so on. But okay, I mean, but if you want, by doing this, you get really an understanding of why there is this commutation. Now, of course, there is a lot of work, and the discovery of Slepian and his collaborator was that this operator commutes, but it commutes with the compression. Now, what we did with Henri was more delicate because we wanted to have an operator which was defined on the full line and which was commuting with these two projections. And this was non-trivial. It was non-trivial because when you work with this, you find out that it's a very delicate problem of self-adjoint extension, because what you have is you have an operator which is symmetric when you take for fundamental domains Schwarz space of Schwarz functions on the line, but it has for Neumann deficiency indices which are 4 and 4. So it's a very non-trivial problem to find the good self-adjoint extension. So this was the start of our work with Henri. And what we found is that the main discovery, first discovery that we found with Henri, which was extremely exciting, was that this self-adjoint operator has discrete spectrum. I mean, I was not expecting this at all. That's why I had abandoned this work in the 90s. And so what we found is that this operator has discrete spectrum. That's an amazing fact, because if it has discrete spectrum, well, this spectrum should be interesting. And it should be interesting in its new part, because there is an easy part of the spectrum which corresponds to what people were doing with the prolate operator and all that, which is the positive part of the spectrum. But the new part, which is extremely interesting, is the negative part of the spectrum. And when we began to look with Henri at the negative part of the spectrum, we found something which, okay, you know, there are few moments in life which are worth living. And what we found is that when we take the semi-classical approximation, so we take, of course, this thing and we look at, you know, we compute the area of where it is in a certain sector and so on, we found that the formula for the number of eigenvalues of the operator begins to resemble the formula that is in Riemann's paper for the number of zeros of zeta, which are less than E. And as I said, you know, this is a typical case where, oh, you begin to say there is something there, okay? Now, we went much further, of course, and okay, you can use elliptic integrals and so on, but this is technique. We use the Liouville transform to transform it into a Schrödinger type problem. And so this is just a Schrödinger type problem. And then we used fine results of the theory in order to compute, to get a precise formula for the number of zeros. And using this formula, now we had a formula very analogous to Riemann's formula, where the term was exactly as in Riemann, with a remainder term which was of the order of log E, and which resemble the best estimate which is known by Trujan for the Riemann zeta function, where there is also a log E term. Okay, and so what we did with Henri, and I have given talks on that, so I will not spend too much time on that, but I just want to remind you about that so that you have the framework. So if you want, this was for an operator, which was this prolate operator, and we gradually realized that the role that this operator is playing is really like the square of the scaling. So if you want, in the negative to positive picture we were getting with Katia, there was a problem with the picture. The problem with the picture is that the scaling does not preserve the decomposition into sonine and prolate part. And the beauty of the prolate operator is that it preserves the sonine space and it preserves the prolate part. So it commutes with this decomposition, which of course is much better because it allows you to restrict it to sonine. And when you restrict it to sonine, essentially you obtain the negative spectrum, which is an amazing fact. Now, with Henri, we knew this result only up to finitely many eigenvalues, but now, as I will explain at the end of my talk, with recent work by Ramis and his collaborators, they seem to know that it's exactly correct. So now what we did with Henri was to extract a square root of this prolate operator in order to get a Dirac operator, because, I mean, of course, you know, the spectrum of zeta looks like a Dirac operator. And I mean, of course, a Dirac operator is much more suggestive of a spectral triple. So it took us a lot of time to get this Dirac operator because, and we used stuff which in fact is called the Darboux method, and which was developed in the 19th century, where this allows if you to factorize the operator, which is the prolate operator, into a product, and then to use the 2x2 matrix technique. I mean, to factorize, you need to solve a Riccati equation, but all this can be done. This is technique. And then you get a Dirac type operator, okay? And when you look at the spectrum of this operator, you find exactly what you would love to have, namely that you have the number of zeros, which is exactly as in Riemann. Now, when you do that, this is abstract stuff. Now you have to go back to the working pad, okay? And you have to do computations that you do with the computer again, okay? And so, I mean, when you do these computations, they are done in a very kind of unsophisticated manner, which was the following. The computation was done by taking the solution of the differential equation corresponding to a putative eigenvalue near lambda taking the solution of the differential equation corresponding to the putative eigenvalue, starting from infinity, namely verifying the boundary condition at infinity, and see if these two guys actually meet. And you look at an intermediate region, which is around 1,000. So here, for instance, for -65, they don't meet. But when you look, for instance, at -38, they meet up to sign, of course, but okay, I mean, up to sign, who cares? You can, of course, change the sign of one of them. So here they meet. And then you keep doing that. And for instance, for -93, they meet. And so what one is doing, by doing this, if you want, one is doing this experiment, and one has the pencil and the paper, and of course, these numbers were in fact integers. So what one does is to take note of when they meet and when they don't meet, which is, of course, extremely rough. Okay. Now, what happens is that very recently, Jean-Pierre Ramis and his collaborators were Françoise Richard-Young and Jean Thomas, have applied the beautiful theory of Ramis on the Stokes phenomenon and the differential Galois theory. And I mean, they have, among the results which they have, which, I mean, I cannot talk about because I don't know the results, but among their results, they have been able to truly compute these numbers, which I was computing, if you want, in this extremely approximative manner. And then I show you the table of comparison. Here I had my poor integers, -39, okay? Okay. And here's their number. So you see their number is -39.383216574467. Okay. The next one I had was -94. They have -94.280833. So, this is, of course, extremely reassuring because it shows that, well, sometimes I'm really wrong. I mean, for instance, I had -211, and they have -214, and then 006, and so on. So, of course, this means that my hand slipped on something, okay? Then they have minus, and so on. But what happens then is the following, is that then they compare it, of course, by doing the thing, with the zeros of zeta, and they find the same type of agreement that we had. They find the same type of agreement that we had. So if you want, they find a remarkably good agreement with the zeros of zeta in the ultraviolet. And I mean, this, if you want, raises the fundamental question on which we are working with Katia and Henri, which is, if you want, one of the few questions that you have to keep in mind all the time. And when you see something in the street and so on, maybe it gives you some idea. But the key is to keep this question all the time in your mind, okay? And the question is the following: how on earth are we going to marry the infrared realization, which is so good, which was using prolate, with the ultraviolet realization, which is so good in the ultraviolet, and which is also using the prolate functions? So this requires an idea, okay? In the best sense of an idea, okay? But what it says is that, in all this work, we are digging hard on the data function, and we are finding marvels along the way. So if you want, and what we are finding each time is that the answer is more subtle than what we thought at the start. And each time we have to understand a new degree of subtlety, which is hidden behind a computation. And for instance, at the moment, we know that there is another degree of subtlety in the guess for the smallest eigenvector, for the Weil quadratic form, involving the prolate functions. Okay, so I think I will stop here, because I'm supposed to talk for 1 hour and a half. And so I have skipped some part, but I think I have more or less reached what I wanted to say. Okay, thank you.
Thank you very much. was fascinating. Okay, Piotr, start with.
So let me begin. I don't really have questions, but I have some answers. So for starters, a very, very big thank you to ALAIN for delivering this talk.
Yes, thank
You
you.
know, my colleagues couldn't give me a better birthday present than your talk. So I'm very.
Well, that's so nice of you. That's
Yeah.
great.
So big thank you, to Ludwig, Tomek, Andrzej, and Mark, many others who helped to arrange all of this. I'm really very happy about it. And now I cannot resist this opportunity to mention two reasons why I love non-commutative geometry. One is very obvious. I mean, because it's fantastic mathematics. It's so diverse, so rich, so multidimensional. You're never bored doing non-commutative geometry. You always can have a different angle. You can always have a different type of diet. I mean, it's very healthy intellectual diet. So this is why I like it. But that's obvious. But another thing is the human factor. I mean, while working on non-commutative geometry, I had the honor and pleasure to interact with so many brilliant minds, with so many wonderful human beings. I mean, this is an incredible adventure. And I'm very proud and happy to be a member of this particular scientific community. It makes me very happy and gives us a big push to go on. I mean, you never want to stop.
Exactly.
So,
Yes. Thank you so much, Piotr. I want to add something. You see, I think what we are in the continuation of the dream of Heisenberg when he was in Helgoland, and when he saw all this, I'm sure. And he was scared by what he saw. I mean, because after all, he had discovered the key point, which is matrix mechanics, and I mean, of course, I mean, so I think what I would like to say is the following: it's the power of ideas. I remember once I was in a dinner, and we were celebrating Catherine Brechignac, who was the secretary of the academy, and it was a dinner where there were several tables, and the people were asked to. It were several tables, so there were lots of people, and people were asked to ask questions, and okay. And so I was thinking about some question I should ask, okay. But before I was given the microphone, there was a theologist who spoke. And this theologian explained that, well, we don't know what happens after death. And so what he said is that even though he had studied theology for all his life, he didn't know, he couldn't say anything about that. Okay. And so I changed my intervention after he said that, So I was eager to talk. And so then came my turn to talk. And what I tried to explain, but in a very maladroit manner, but okay. So what I tried to explain is the following. I tried to explain that, we are confused when we think of ourselves as collection of cells and so on, and a material body. For the following reason, that all the cells of the body actually change, renew themselves after a relatively small amount of time, like 2 years or something. So what I explained was that we are not a collection of cells. We are a scheme, which is the scheme underlying this collection of cells. And moreover, I said in a very blunt manner, Galois is not dead.
Yes.
Because what I said is that, Galois is more alive than anybody I know, because of the fantastic power of his idea.
Yeah.
And so, I mean, I think this is a lesson. And so, I mean, what I wanted to say is Heisenberg is not dead because of the fantastic power of his idea, of his discovery. And I know that, Piotr, you love Galois theory because
Of course.
for very good reasons. But this is a fantastic thing. I mean, think about this guy. I mean, he made this great work when he was 17. He didn't do much work after because he was in jail and so on. He didn't really have time to do much work. He died when he was 20. And his ideas are like a wild horse. You know, they are alive, they are powerful, they are there everywhere.
Yeah.
So that's all I want to say. Yeah.
Yeah.
This is like
Okay.
conservation of information in black holes.
Yes. Yeah, that's what it is. It is the amount of information that we can bring to the human community. It's exactly this. And in fact, you know, there was this birthday of Dixmuir, I should say. It was very interesting because there was, so Dixmuir turned 100 years old in May. And there was a dinner which was organized in his place. And it was very interesting because there was, if you want, a discussion between Serre and Dixmuir on this dinner. And Serre was saying that, okay, we do mathematics, not because of glory or whatever. No, but because of the urge to understand. Okay, and this I agree completely, of course. I mean, you know, there are situations in which, I mean, the whole thing is the urge to understand. And then Dixmuir said, okay, that he said, he was speaking of himself, I do mathematics to exactly to this, to contribute, you know, to the human knowledge and to the progress and all that. And I think, you know, this is so true. I mean, in a way, I mean, we are mathematicians, and I think the best goal we can have is to contribute, you know, really to this progress, which is, and nowadays with ChatGPT and all that, I mean, we have access to so much that we have no excuse, you know. I mean, there is so much we can read, we can access to, and there are lots of things which I'm sure are already there. I mean, you know, I'm sure, completely sure.
Okay. Are there some other comments?
Yes, please. Yes.
Who?
Let me
Sorry.
make a little comment to
Please.
what Alain said about the first coefficient being zero, that condition.
Yes.
It reminds me of cuspidality.
Yes. Yeah, it could have
The
been.
discrete spectrum, so it could
Yeah.
be related to something like that.
Yeah, except that this condition was virtual because it was a mistake in the computer
Yeah,
calculation.
but that's what it says.
Yeah.
Cuspidal forms, not just.
Yeah, sure. No, I agree with you. And in fact, it's a good condition. That's what we found out in the Toeplitz case. It's a good condition. It was not, you know, it's a condition that actually makes the function more easily tractable. But yeah. But if you want, I hope I tried to convey the fact that this Riemann zeta function is a gold mine, you know. It's really, I mean, one has to explore, one has to go. And it's always more subtle than what it looks like from the outside. I mean, and there are misgivings. There is another misgiving which I didn't explain, but which is a very common misgiving. Because some people tell you that the reason for looking for the Riemann hypothesis is to have a formula for the number of primes less than n. Now, the story there is that when I was in high school, at some point, my teacher told in the class, I think it was in La Seconde or something like that. It's 2 years before baccalaureate. So my teacher said, there is no formula for the number of primes less than n. Of course, I mean, I knew that he was wrong because you can always concoct a formula, a stupid formula. Okay. So, I mean, the next day I came to him with a formula which was 2 pages long, which was, of course, a stupid formula. Okay. But it was a formula. And then, then, of course, I mean, you can say, and this is the usual misgiving of people, there is no simple formula for the number of zeros less than n. Now, I claim this is wrong. This is wrong, and in fact, I published a paper in which I gave the following formula, and you will accept that it's a simple formula if I can tell it. Okay, and when you write it down, it takes less than a line. It takes half a line. Okay, so the formula is the following: the number of prime less or equal to n. So n is given to you, okay? What is it? It's the sum from 1 to n. It's the integral part, sorry, of the sum from 1 to n of sine square of pi over 2 multiplied by gamma of k over k. I claim this is the true formula. That gives you, for any n, the number of prime less or equal to n. Warning, if you want to use this formula for the computer should know a lot of decimals of the number pi. Because this formula does depend on a lot of decimal points of the number pi. And if you replace pi over 2 by a number x, what happens is that for almost all x in the measure theory sense, formula behaves like essentially like n over 2. And for almost x, all x in the bare sense, it behaves like the number of primes, up to a factor. Okay, there is a factor depending on what is. So you see that this is a misgiving that many people have, that there is no simple formula. Now, challenge for physicists. Challenge for physicists. Of course, I mean, this is putting the bar very, very high. Challenge for physicists. Write this sum of sine square as a Feynman integral. After all, it's a sum of exponential of imaginary numbers. Okay? And get something out of that. All right? I mean, and if you do that, you will find out that it shows you how subtle the Feynman integral is. See, because here I have a sum of exponentials of I pi over 2 times gamma of k over k. Okay, essentially, I mean, you know, up to a small variant. And it all depends on that. And if you look at the Feynman integral, you will find that it's extremely subtle because of the I epsilon prescription of Feynman, which many people totally overlook, and which is in fact a way to Vic rotate. So if you want, when you hear people talking about the Feynman integral, in general, they don't know what they are talking about because of this I epsilon prescription, you know, because of the Vic rotation. So there are plenty of, you know, things which are very interesting to learn about, and okay, which are connected to that. And I think, you know, it's. I mean, I remember also there was a conference in Mondovi recently, and about Grothendieck. I mean, about topos theory and all that. And I mean, people were saying that. You know, Grothendieck was like, I mean, they were not realizing that Grothendieck had been inspired, of course, very importantly in his work by the Veil conjecture. I mean, you know, people get inspired by problems. It's very important. Kummer was, when he discovered ideal numbers, of course, he was inspired by the Fermat problem. So, I mean, you know, there are all these reasons to I mean, you know, to get some strong inspiration. So there are these two sources of inspiration. There is a source of Galois, like, you know, great ideas, which have fantastic power, and stumbling blocks, you know, problems that you cannot solve. Because, okay, if we could solve every problem, okay, this would be so boring. I mean, you know, but it's not the case. And there are stumbling blocks, and there are stumbling blocks which are so great, you know, that by their strengths, they force you to go deeper and deeper and deeper in the stuff. I mean, and, I think that's richness. You know, I think I mean these type of problems which are, you know, sort of which have fascinated people, and they are fascinating exactly because of this, because they are, if you want, they are, and there is of course the wrong side of the medal. The wrong side is the following, is that it was proved by Gregory Chaitin that if you list the mathematical truths, namely the things which are true, okay, And among these, you ask which ones are provable. The proportion tends to 0. So of course, this is a warning, you know. That's a big warning that we need to be we need to be careful about such things. But yeah,
It contradicts Hilbert's epitaph.
yeah, of course, but it contradicts it in a very concrete manner. You see, Gödel's theorem can be taken as abstract and so on, and you can say, wow, whatever I will work on, it will be a problem which is solvable. No, I mean, what Chaitin gives you is, you know, a statement which, and probably what it says is that you have to use fancy stuff. Because, for instance, you know, there are these statements which are improvable in piano arithmetic, but which are true when you use ZFC. But of course, then you have to use fancy stuff. So, I mean, okay. We have to use something like the Dix-Mitre. Yes, yes. Okay, guys. So thanks a lot for listening. Thanks a lot for your attention. Yes. Yeah, you have some questions? Some more? Yes, please.
More questions? Or maybe comments?
If I could ask, I would like to ask some questions.
Ah, yes, I was so sorry not to hear you, you know. Yes, because normally you have a lot of nice questions. Yes.
But
So Adam, please.
I'm not sure about my internet connection, so forgive me if you would.
Oh, it's okay. I can hear you. Yes, yeah.
Okay, so I would ask you about this behavior of this function, counting function. So
Yes.
this grows like times log e. So what is the right way to think it about it conceptually?
Okay, let me explain. Let me answer. Let me answer. This is the part which I didn't show. This is the part of the heat expansion for zeta. You see, what you are saying is that if it were a spectral triple of the usual kind, if it grows like E log E, what does it mean on the heat expansion? What does it mean on the dimension spectrum? What it means on the dimension spectrum is that 1 is in the dimension spectrum, but it has a pole of order 2. That's what it means. And in fact, I didn't show in my slides, but I published an article on that you can actually compute the first terms of the heat expansion. In fact, for zeta, you can compute all the terms of the heat expansion, and you can compare it with the prolate, with that what we did with Henri, and you get the same terms. And these terms are extremely subtle, because the coefficient that you get for the double pole is something like you have the log of 2 pi, and you have the Euler constant and all that. So it's really quite subtle. So this is the answer to your question. So it means, if you want, of course, it's not a spectral triple like a circle. It's something quite more subtle because of this double pole.
So this dimension spectrum is like 1 plus epsilon or 1 minus?
Exactly. Yeah, no, plus. It's 1 plus epsilon. Yeah.
Okay. Okay, and another thing related to this spectrum is the fact that you have some spectral triple which is defined on the whole line, but nevertheless the Dirac operator has compact resolvent, and this
Oh yeah,
is
no,
not in the.
that's okay. No, that's okay,
unusual.
because when you look at the corresponding metric, you have to look at the corresponding metric. And the corresponding metric is not the metric of the usual line. So, I mean, you know, so this is the difference. When you look at the associated metric, you will find that it doesn't look like a line, you see. There is a singular point and so on. So I mean, this all depends on the associated metric, yes. Yeah, but that's a good question, yes.
Okay, thank you. And maybe one last question related to your paper about the second quantization and also of fermions, this notion of second quantized spectral triple.
Yes.
And as far as I remember, also zeta function appeared there, but I don't know whether there is some relation
the
between
connection is
those
totally different.
work which
Yeah, you are
explained.
right, of course. No, there, it's like, you know, there is a devil which puts some zeta function, boom, like it pops up. So there it popped up for a totally different reason. It popped up because of the fact that it gave, if you want, very specific test functions to apply the spectral action. And then when one was computing the coefficients that one gets from this spectral action, it was delivering the value of the zeta function at odd integers. Okay, which is a different story. Yeah. So this was quite surprising, of course. Yeah, extremely surprising. Sure.
Okay, thank you.
Other questions or comments? May I ask a question? Okay.
Oh, please ask.
I have one question about your arithmetic side.
Ah, yes, okay.
So there were some approaches to analogs of zeta function in positive characteristic in
Sure.
algebraic geometry or pure arithmetic geometry.
Sure.
And the solution to the problem was introducing intersection theory on arithmetic surfaces.
Yes.
So now you have something of geometry, your arithmetic side, with a place at infinity.
Yeah. No,
Can you
let me
envision here something?
Yeah, no, of course. Let me answer immediately. So the answer is the following. The answer is that what replaces the curve is what I showed. Namely, it is a scaling side.
Mhm.
Scaling side has a visible part, which is exactly the same as what happens in the case of finite characteristic, with the points of the curve over the algebraic closure of the finite field. It looks exactly right. But it has a flash around that, because it's a non-commutative space. That flash is absolutely necessary, otherwise you wouldn't get the correct veil terms, which, because they are more subtle, cannot be obtained as in the case of function fields. Now, what replaces the square? You are right to mention the square of the curve. What replaces the square of the curve and the analysis on the square of the curve are the Schwarz kernels of operators operating on the scaling side. And among these Schwarz kernels, there is the Schwarz kernel for the scaling operator, which plays exactly the same role as the Frobenius correspondence in the case of function fields. So we have a full dictionary between at the geometric level, what corresponds to what, and so on. So if you want, at the geometric level, especially now after this business with the covers and all that, we have really a full dictionary, because with the covers, what we get is not only the points over the algebraic closure of the ground field, but we also get the abelian extensions. So if you want, at the geometric level, we have the picture, okay? And we also have what replaces, if you want, the intersection number of divisors and all that. But, okay, what is so, if you want, specific about the Archimedean place, all right, is what requires all this analytic work. So all the analytic work is coming from the uniqueness of the Archimedean place. And what the part of my talk which I didn't show is entitled A First Glance at the Archimedean Place, in the sense that we hear the Archimedean place from the heat expansion. And from this hearing, we can guess what it looks like. And you know, so this is another talk. But in Cortona, I gave this talk.
So the sound of infinity.
The sound of the Archimedean place.
Okay.
Can we hear the shape of the Archimedean place? And we can. That's the beauty.
Okay. Maybe one more question. How could you compare your approach with this philosophical approach of defining everything over one element field?
No, but that's the same. So if you want, no, but it's the same, because in what we do with Katia, we were guided by two things. If you want, the arithmetic side is like the ultimate geometric point, but the ultimate coefficients are what we developed with Katia, namely coming from the gamma rings of Siegel and from the sphere spectrum and so on. It's a combinatorial counterpart, which now is gaining ground among the people working in topology. I mean, with Kadia, we have a lot of trouble, having this accepted, but we wrote a paper which is very comprehensive, which is in the honor of Manin, and in which the title of the paper is inspired from André Weil, and it's called On the Metaphysics of F1. There are these beautiful statements from André Weil about the metaphysics of the equations at the time of Lagrange, before Galois, on the metaphysics of this and that. And F1, for a long time, has been in a state of metaphysics, but with Katia, okay, we believe that we have found the ultimate coefficients and that they will gain ground. They will gain ground.
Yeah,
it will take time, but they will gain.
If I might add a comment related to this point, is that this idea that Weil had, that function field, as you know all, I think, at this point, function field and number field should be comparable in the sense of, in the number field case, to have an absolute, as we say now, theory of coefficients involved. What ALAIN spoke about today with the scaling site and its abelian cover, absolute abelian cover. So this is the geometric part. If we were in algebraic geometry, we would say the topological space. Like in scheme theory, we have a topological space and a sheaf of structure sheaf. So what ALAIN spoke about today is a vast generalization of the notion of scheme, but for the topological space, for the theory of coefficients, so what topologists have developed with the sphere spectrum, it's very interesting because it's characteristic free. So when we speak about the Archimedean place, in a way we are over the Archimedean place. I mean, with B, with the theory of F1 as originally thought, with idempotent structure that they sort of enlarge the category of commutative rings, so in particular Z. So we went below Z, or in a way categorical meant extend the category of commutative rings with these idempotent semi-rings, and in particular there is at the bottom this Boolean. But the Boolean has still in it has a very nice point of view, which is something below the Archimedean place in a way, which recasts information of the Archimedean place. But the Boolean has still a characteristic attached to it. So it's what we say characteristic one, or what algebraists would call idempotent structure. But if we seek for absolute geometry in terms of coefficients, it should be characteristic free. And so this is what we went through with along the tour by implementing the same idea that Grimm-Siegel had since the late 60s with these gamma rings or gamma sets in particular. So these are structures that understood at the categorical level without moving to the homotopic, more sophisticated viewpoint, are very, very good to represent an absolute theory of coefficients. And in particular, because any classical type of category that we use in algebraic geometry, like commutative rings or even monoid, semi-rings, they all fully faithfully embed in this new vision where the classical algebra in terms of sets with operation is replaced by a theory of categorical framework, categorical type of construction with the functors and the operators among functors. So this is very, very interesting. And I think here we have a strong group in homotopy theory at Johns Hopkins, and they start to realize the importance of this understanding, basic understanding of the sphere spectrum. So they take immediately the homotopical viewpoint because they are interested in having a pi 0, which is a group, excuse me. But we instead we are concerned more at the really fundamental understanding of this important structure in homotopy theory, which is the sphere spectrum, in fact, the localization of the sphere spectrum. So to have something which is characteristic free that has to be associated to the geometry that is represented by the scaling site of the Adelic space as ALAIN is telling us today. Excuse me to be so long.
Thank you very much. Okay, so now we see how wide is the vision of Alain Kohn of quantitative metaphysics. So thank you very much for a beautiful talk.
Thank you, guys. Thank you, guys. I'm really grateful.
Thank
Yes.
you. Thank you. Ludwig, last faculty.
Thank you, Ludwig. Yes.
So not. Thank you. Okay.
So Ludwig will raise now a toast.
Oh, very good, guys. Yes, yes.
So-
Wow.
What do you
Don't
have in
take
your glasses?
We drink
Both
Both
Okay.
to Piotr and to ALAIN.
With the legal
Okay.
word.
Thank you so much. Thank you for coming. Thank you, everybody. Thank you.
Thank you, guys. Yes. Great.
Thank you.